I think I'm being made sport of. Maurice, what do you think? You think they're making sport of me?
Yeah.
I think so. You know what they did with Samson? They made sport of him. And we'll see. So he pulled down the columns, right, in the temple. I have the grade book. Don't do it. So to provide modularity, make effective use of the distributed hardware. Notice this, they have to partition the operating system into disjoint utilities that communicate with each other. How? Via messages. So right off the bat, as soon as you get outside, as soon as you have distinct pieces of hardware talking to one another, almost always the communication mechanism, okay, is going to be through message passing. Okay, it's just the more efficient way of doing it. If it's on chip, then you can deal with shared memory partitions and semaphores. When it's off, when it's two separate machines, almost always it's message passing. Now, they do have some highly specialized machine. Silicon Graphics, SGI, for example, has a set of machines that have what they call a NUMA, non-uniform memory access. A NUMA architecture, whereby to the programmer, it looks like all of the modules, all of the nodes have the same memory space. But under the covers, it's implemented with message passing. Okay? So they have specialized hardware that makes that message passing more efficient, but still, under the covers, it's almost always message passing, unless it's on the same chip, where you can have a hardware connection to the shared memory buffer. So,
is message passing kind of like similar to remote procedure call?
it's so a remote procedure call could be viewed as a kind of message. Yes, it could be viewed as a kind of message. It's a slightly different deal in the sense that a remote procedure call is a generalized function call. Most message passing interfaces have a specific set of primitives. These are what you use. You know, send, receive.
Right.
In a message passing interface, you wouldn't say, calculate cosine of x on this data.
Right.
Whereas with RPC, you could. Okay? But in some very generalized idea, a remote procedure call, in the sense that it goes to another box to do something. But, all right, so anyway, disjoint utilities communicate via messages. Now, it says to take advantage of the parallelism present, by the way, real parallelism here, right? This is not fake uniprocessor parallelism that's mimicked via short time slices. This is true parallelism. Okay, good. So to take advantage of this and to provide the robustness, so what's the problem with true parallel programming?
It's not actually.
Well, there's a lot of overhead.
There's overhead, but you don't know what order things are going to happen in.
Right.
Okay, and you can lead to deadlock. You can lead to
starvation.
You can lead to unintended race conditions.
Yeah.
Parallel programming is significantly more difficult to debug because not only do you have the use cases, okay, but then you have what order did they occur in. What happened while I was doing this?
That was one of my questions when we read this was, what about the validity of the information after all these?
Yeah, so it's parallel debugging is, I mean, it's a shot in the dark. You just, you kind of hope it's right. I mean, it's tough stuff. So, and to provide robustness, okay, it says all programs, including utilities, are task forces containing many concurrent cooperating activities. All right, good. So let's move on, see what else this says. All right, so. Put my spectacles on. Good. So, introduction, Medusa, multi-user operating system under development for CM Star, a multi-microprocessor system recently completed at CMU. Okay, they want to understand, okay, when you distribute the operating system, you want to do it in a way that takes advantage of the hardware, okay? Takes advantage of the hardware. Okay, good. So Medusa is the second operating system for CM Star. The first system was Star OS. Good. And then you talk a little bit about Star. Maybe that's where the Star came from. So, well, it says Star OS, so maybe CM Star was a twist of that. Okay, so it says Star OS. So this is sort of history. Embodies a general object addressing mechanism and a set of tools for manipulating parallel programs. It says for Medusa, we've chosen to emphasize problems of structure rather than facilities. The goal of the project has been to gain an understanding of how to build distributed operating systems and to exploit the hardware to produce a system with three pieces: modularity, robustness, performance. Okay, sort of a three-legged stool. So modularity, large number of small cooperating subcomponents that may be built, modified, and measured independently, okay, as opposed to this big mess. So you got these little pieces that you can tweak.
Are these separate machines or are these all on one machine?
No, these are separate machines.
That's what I'm thinking.
I haven't read it recently, but it's probably gonna. They're probably gonna be PDP-11. So let me look. Yeah, LSI 11. Yeah, so they're the PD. So the LSI 11 was Digital Equipment Corporation's microprocessor, and LSI 11. All right, it was programmed in Macro 11 assembly language. All right, one of the earliest microprocessors. Anyway, back to here. So they didn't get PDP-11s and glue them together. It looks like they built them using LSI 11 chips. All right, good. So modularity, good. Small cooperating subcomponents can be tested, built, tweaked independently. Okay, and of course that, as they point out, complements the CM Star hardware because this results, if I have a bunch of small modules, this results in a large number of small processors. Okay, so I've got a bunch of small processors, each running these little tiny programs. It's kind of a nice match. Okay, it's kind of a nice match. Yes.
So what are they talking about when they say the K-map cluster? I mean,
I haven't got there yet. I don't know yet. I'll have to look. I believe it has to do with that they're taking a piece of hardware that's going to map to a certain number of processors, and then there's a sort of inner circle. So that's my guess. It's probably going to be, based on this diagram, some type of a star topology, okay, with a central hub, okay, and then these individual bus processors out here. So my guess is the K-map is basically going to say this guy talks to these K processors, this guy talks to these K processors, and you can see that it's this sort of a star topology where I can't. So for example, I can't go directly from here to here. I have to go into the star and then out. That's my guess. Again, it's been since last term. No, we didn't get this far in this paper last term. So it's been over a year since I read it. I don't remember.
But Dr. Morris, and he was talking about each one of them processors supposed to have some kind of record of the mapping, so they wouldn't have to go to one processor. But wouldn't that produce some kind of security issue? But if each one of them had a copy?
So security is always a problem. Anytime you go out on a piece of wire, security is a problem. But even if you don't go out on a piece of wire, security is a problem. I mean, we infiltrated the Iranian, what are they called?
The reactors?
They were producing enriched uranium in these, darn it, my mind has gone blank. It's not cyclotrons. Particle accelerators, I think they're called. I mean, we infiltrated
the Hadron accelerator?
Huh?
The Hadron ones?
I don't know what their structure is, but somehow the United States and Israel conspired to infiltrate into the Iranian nuclear generation program using flash drives. So you don't even have to have a physical piece of wire. Security is always an issue. It's always an issue. I don't know if this paper addresses it directly, but let's get back to So after modularity then is the idea of robustness, okay? So the idea here, so robustness has to do with the way it responds to change. All right, if something goofy happens, if something different happens, does it break? Okay, there's nothing worse than a brittle piece of software. You know, you upgrade the operating system, you know, Microsoft says, here's the next hot patch. Okay, and you hot patch your operating system, some little dinky thing, and your code breaks. Okay, brittle code is just no fun. And then you go back to the vendor. Well, we're looking at that, and you're 6 days out of business or 6 months out of business. My credit union at Wright-Patterson Air Force Base recently upgraded their web services. Okay, so I'm trying to get to my bank account for 3 days, and I can't. Finally, I go hop in there, and it says, due to a security issue in iOS 6, you cannot get to this website using an Apple device or an iPad or an iPhone. And I'm thinking, then why did you allow the upgrade to take place? You've just eliminated
Majority of your
I would
customers.
guess half your users.
Yes.
You know, at least half the people are using iDevices, whether they're iPads or iPhones, is ignorant as far as I'm concerned. It's just flat out ignorant. They shouldn't have deployed.
Somebody losing a job, ain't they?
So anyway, systems should be able to respond in a reasonable way to changes in its environment. So, things such as changing workload, things such as the hardware breaks, things such as somebody changes, well, firmware or software. So firmware is software that's in a programmable device, whether it's a EEPROM or whatever else, right? It's called firmware, because it's not as easy to change, but it can be changed. So it's sort of the same as it's sort of the same as software, but not quite. Okay, so software, firmware changes, all of these, okay? And so they're saying it should be robust. Comment?
That's a book I left with somebody you last.
Oh, okay. And the third is performance. I mean, if it's really modular and it's really robust, but it takes too long to run, it's not going to sell. So they're also looking at performance. And by the way, both modularity and robustness, okay, impact performance. Okay? So the more robust you try to make it, and the more modular you try to make it, so if it's hyper modular, what does that translate to? A bunch of function calls. A bunch of function calls. Well, guess what? There's an overhead for making a function call. You got to push everything on the stack, okay? Save the registers, load up the parameters, okay? Set the program counter to the return address somewhere, okay? Set the program counter to the target address. When it gets there, restore. All right. So, performance. Both the structure of the operating system and the abstractions it provides to user programs should reflect the underlying hardware. Application programs should be able to run with approximately the same efficiency using Medusa as they could have on the bare hardware. That's a tall order. So what they're trying to do with Medusa is they're trying to build at the base of the operating system, in effect, a virtual structure that causes the layer that the rest of the system sees to look like the bare hardware. And that's a tall order. That's hard to do. All right? And that has to do with performance. All right? Good. Let's see. Okay, so the system software required to achieve, blah, blah, blah. Okay? 2 general attributes have been especially, first, the physical arrangement of the hardware. For each processor, there is a small set of local resources that are accessible immediately and efficiently. The other facilities in their system are also accessible, but with greater overhead. So as an example, if I have a CPU sitting here, and it has what's the principal resource you usually think of with a CPU?
Physical memory?
Memory, yeah, RAM. So we use now RAM. If I got one CPU there, another CPU over here with this RAM, okay? The idea is that I layer on top of this thing the illusion that it's a bigger CPU with a larger piece of memory.
Now we're talking about distributed systems, right?
Please?
We're talking about distributed systems.
Yes, so this is the illusion that's created on top. And so in this case, this local processor has very rapid access to this RAM. This processor has access to this RAM, but much slower.
Through that.
Through some type of interface here. Through some type of hardware/software interface.
Hardware too?
Of course, yes. Any distributed system
Yeah.
implicitly implies there's some hardware infrastructure to facilitate the integration of the
There have to be
distributed
some
pieces.
sort of Ethernet, right? Because
Probably, yeah, some kind of a bus or a network or who knows? Who knows, yes. I meant to bring it today and I left it at the house. I've got a Cray C-Star chip. It's a 3D Torus interconnect. It's got 4 chips on it, so anyway, specialized hardware that Cray builds to make their processors talk to one another much more rapidly than over, say, off-the-shelf InfiniBand.
Have you seen it in
Or off-the-shelf
operation?
Ethernet. What's that?
Have you seen it in operation?
Yeah, every day,
So is it really, really fast?
of course. That's why we spent $20 million to buy it.
Oh, snap. Yeah, it's fast.
Yeah, we're getting ready to get one of the world's largest Cray systems, 150,000 cores. 150,000 cores. It's a hoss.
what's the current record right now?
Huh?
What's the current record right now for the cores? I think it's
Oh, I don't know. It's
70,000
well
cores.
above that. It's well above 150,000.
really.
Oh, yeah. Army's small change. DOD's small change when it comes to supercomputers. You go to like Department of Energy, their nuclear program, or when they're doing very large simulations of nuclear phenomena on a femtosecond time scale.
Mhm.
You know, we're doing like millisecond time scale simulations, you know, and it still takes weeks to run. And when you're doing femtoseconds to understand, you know, nuclear reactions and stuff. You know, what's the collider? You do a simulation of a collider, when the particle hits.
Mhm.
I mean, it boggles the mind. They have systems. So in America, the big supercomputer folk are the DOE. And then all kinds of foreign countries are now very much in the mix. China has, in the past several times, they've been either at the top or very close to the top of what's called the top 500 list.
Yeah.
It's sort of an artificial measure, but
In Japan too, I mean.
yeah, the Earth Sim.
Oh, yeah.
The Earth simulator was a two-story building, and the upper floor was the processors, and the lower floor was the full crossbar switch.
That's
So
where
they
the
could
Earth
talk
Sun
to
1
one
or
another.
2.
Huh?
Because they built 2. They built one in 2004 and one in 2008, I think.
Well, whichever, I don't know which one I'm speaking of, they're probably housed in the same facility,
Uh-huh.
but it was, I mean, for a while, you could add up everybody else on the list, and it still wouldn't beat them.
Yeah.
It was a hoss. I think it had Fujitsu.
NEC.
Was it NEC?
Yeah.
Okay, I didn't know if it was Fujitsu or NEC. So, yeah, it was a hoss. They were trying to do simulations of like global atmosphere, global ocean modeling.
Earthquakes.
Okay, I mean, you know, you need a lot of compute to do that. Yes?
I have a question. What's the purpose of a supercomputer? I know we're not into like ones anymore.
What's the purpose of a supercomputer?
Like, yeah, what's the, like, they have the world's fastest right now, which is Sequoia, but like,
Okay.
I want to go see it, but I don't really.
So why do we use it?
Yeah.
Okay, here you go. So, Umar, when you don't get your way, okay, you go blow stuff up, right?
Yeah.
Isn't that what you do? Isn't that what you do? When you don't get your way, you go blow stuff up, right? And of course, everybody in the room is going to say, of course not, because rational people don't do that. Okay, but you know what? We got a small group of people. You got people that think God's given them the right to blow up abortion clinics in this country because they don't like abortion. God told me to go kill the doctor. No, he didn't. No, we didn't. So we have to protect, the DOD has to protect this nation and its allies against this kind of lunacy. Now look, how do you know how to protect, say, New York City against, say, some type of nerve agent that gets dumped in the atmosphere? Oh, I know. We'll go out in the middle of the Mojave Desert, and we'll build a full-scale model of New York City, and then we'll arrange the weather pattern so it's the same as New York City, and we'll dump the nerve. You can't do that, right? So, right. So come up here a minute.
Jackson State got a pretty good one over there too, right?
It's not bad. It's not bad. So come over here. So, Physics 101. So stand right there. So no, I'm not going to hurt you. I won't hurt you. I won't hurt you too badly, okay? I promise. So right now, in the reference frame being the room, Ashley is at rest. What does that mean?
It's not moving.
It's not moving.
The sum of the
All the forces
The
working
forces
on
are
is
zero,
Yeah.
and the moments are zero, right? Because she's not moving. But if I were to impart an acceleration, what happened?
She moved.
She moved, right? Thanks. So F equals ma. So we have physics that can, with certain simplifying assumptions, produce reasonable answers about what we see in our environment, right? So what you do is, I want to understand what happens if someone sets off a device outside the federal building in Oklahoma City. Okay, what was his name? Timothy McVeigh.
Yeah.
So Timothy McVeigh, God told him to go kill a bunch of innocent people, I guess. I don't know, he's a loon. All right, so Timothy McVeigh pulls up in front of the federal building with a truck filled with chicken shit and diesel fuel, which translates to
Bomb.
explosive, all right, and blows up the building and kills a bunch of people. All right, so when the explosive goes off, what is that? That's an acceleration. Okay, so we have some people who experiment and perform analyses of what kinds of accelerations do an explosion produce. So that's a piece of science that we have. We got another person that says, what's the structural integrity of this kind of steel when it's got this kind of concrete on it, when it's covered with Kevlar? So we got another piece, and then ultimately you get enough little pieces of science put together to where you can build a very large physics-based model and simulation. And you say, okay, at time 0, and then you discretize this large three-dimensional space into x, y, z coordinates, so it's not continuous, same problem. You discretize it into three-dimensional space, and this gives rise to very large sets of sparse linear equations. How do you solve sparse linear equations? What's the technique? Tawanta. What's a good technique for solving a set of linear equations?
You simulate them?
An order n cubed algorithm for solving linear equations. No, come on. No, come on. Somebody's elimination. Gaussian elimination. Use LUP decomposition to solve the set of linear equations subject to the accelerations that are in the system. So for each little point in this system, each little point has on it the current set of accelerations, the current set of moments, blah, 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 right? You run the simulation for, say, 10 milliseconds, okay? Plug in the boundary conditions, and now what do you have? A new set of forces, a new set of moments, right? So you advance one time step, 10 milliseconds. Now what do? I discretize this new system into a three-dimensional mesh. Okay, it produces a large system of sparse linear equations with a new set of boundary conditions, and I solve it. It marches forward another 10 milliseconds, and then I do it over and over. So in the course of, say, a 2-month run, I might be able to get a 45-second view of what happens when some device gets let off.